Hello, everyone. Welcome to the first webinar in 2025. Today, we have the honor to have Professor Song Mei from UC Berkeley. He is an assistant professor in the Department of Statistics and the Department of Electrical Engineering and Computer Science. He just received his PhD from Stanford in 2010. Dr. Mei's research is motivated by data science and AI analysis and the intersection of statistics, machine learning, information theory, and computer science. His research interests include language models and diffusion model, theory of deep learning, theory of reinforcement learning, high-dimensional statistics, quantum algorithms, and uncertainty quantification. Dr. Mei is a very talented young researcher and has done a lot of important works. His research has both computer science aspect and statisticians aspect, where he tries to provide theoretical foundations and insights for many of the black box models, like in deep learning and large AI models. Actually, I never met him before, and I got to know him through his work, Transformers as Statisticians in NeuroNIPS in 2023. Dr. Mei's work has got recognized by both academia and industry. He is a recipient of NSF Career Award, an Amazon Research Award, and a Google Research Scholar Award. So without further ado, let's welcome Dr. Mei.
Yeah, thank you, Zhihua, for the kind introduction, for the invitation, and thanks for the audience. Motivated by the recent development of generative AI, so today I would like to rethink about the role of neural networks played in these AI systems. This talk is based on joint work with Yu Bai, Fan Chen, Yuchen Wu, Huan Wang, and Cai Mingxiong. Traditionally, statisticians view neural networks as function approximators, specifying the connection between the input X and the output Y. Traditional textbook result says that one hidden layer neural networks are universal function approximators, which can approximate any functions. In terms of approximation efficiency, textbook results says that neural networks efficiently represent smooth or low-dimensional functions. But for high-dimensional functions, there may be curse of dimensionality in the worst case. By curse of dimensionality, I mean that suppose we want to use neural network to approximate a target function in d dimension. To achieve epsilon accuracy, it's required that the number of neurons to be exponential in dimension, unless the target function is super smooth. So the curse of dimensionality is definitely a very negative result in neural network approximation theory. And theoretical researchers, tried different approach to resolve this issue using by exploiting the structure of the target function, including like smoothness or low dimensionality. And now we enter into the age of generative AI, and we found that while this traditional function approximation viewpoint has encountered some challenge. For example, in diffusion models, people are using these neural networks, especially like this UNet, to approximate the denoising function. And this denoising function has high-dimensional input and high-dimensional output. So the traditional function approximation viewpoint may imply a curse of dimensionality of this neural network that is hard to overcome. So it says like it requires like a huge neural network and huge sample size to learn this denoising function, which is not what we observe in practice. And for language models, people are using these transformers to approximate these transition probabilities from a couple of words to the next word. So these transition probabilities are super high dimensional functions with high dimensional input, and even the input dimension is varying. So it's not clear how this classical function approximation theory can explain the effectiveness of these transformers in language model. So to theoretically explain and understand the effectiveness of neural networks in these generative AI models, I would like to propose a new perspective on the role of neural networks. I would like to say neural networks are algorithm approximators going beyond the function approximation. So here, this statement seems a little bit abstract for now. So let me first explain this statement through the example of language model and diffusion model. And after that, I will discuss the difference between this function approximation viewpoint and the algorithm approximation perspective. Okay, so let me first talk about the example of language model. So language model like ChatGPT nowadays are super powerful, and one powerful capability of this language model is called the in-context learning. So here is an example of in-context learning. Is an interaction of me with ChatGPT. So I just prompt a sentence, apple to fruit, sofa to furniture, and bird to question mark. Then the language model answers me animal. So the reason of this interaction is the following. So apple belong to the category of fruit, sofa belong to furniture, and bird belong to the category of animal. So it seems that this ChatGPT, this language model, is capable of learning some prediction rule in the demonstration example, and then applied the learned prediction rule to the additional input. So people call this capability in-context learning. It is first discovered in this paper. This is the GPT-3 paper by OpenAI. And they call it in-context learning because this learning seems to happen in the context of this language model. Mathematically, you can think about this language model is a huge neural network called a transformer that is meta-trained with a huge metadata set. And we say that this transformer is capable of in-context learning if the following thing happen. Suppose there is a dataset xi, yi, which are IID following some distribution P, where this distribution is unknown to this transformer. And we concatenate this dataset xi, yi into a single sequence and append the new x as a context input. And suppose this transformer is capable of return an estimator y hat that is a good estimator of the new y, then we say that this transformer is capable of in-context learning. So in this example, this apple is x1, fruit y1, sofa x2, furniture y2, bird x3, and the animal is y3 hat. So this in-context learning is very similar to supervised learning. It's just that this supervised learning is happening in the context of this transformer. So people call it in-context learning. For people who are familiar with the meta-learning paradigm, this in-context learning is actually more similar to the meta-learning. In meta-learning, there are also this meta-learning phase and adaptation phase. The difference between in-context learning and meta-learning is that, well, for in-context learning, in the adaptation phase, there is no parameter updating of this neural network. You just put this xi, yi, this new data set as the context input to this language model, and then it, without parameter update, it just return a new y hat, which is a good estimator of the new y. So this is like intuitively what is the in-context learning paradigm. And in 2022, a group of theoretical researchers, they want to understand better the in-context learning capability of transformer. So they perform some experiment on a synthetic data set. So they look at the Bayesian linear model, which is a very simple statistical model, where there's a data set xi, yi, y is a linear function of x with parameter beta, where parameter beta has a Gaussian prior, and x and the epsilon, the noise and feature, they're also Gaussian. So this is a very simple Bayesian linear model task. And what this group of people, this theoretician, what they do is that, well, they concatenate this xi, yi in this data set into a single sequence and call this sequence a metadata point. And then they generate a metadata set. Well, a metadata point has length capital N. And then they generate a metadata set of size little n by generating ID samples from this metadata point distribution. So there is like there is little n number of metadata points, and for each metadata point, it has capital N number of data points. Well, for data points in the single metadata point, they have the same parameter beta, but for different metadata points, they have different parameter beta, all following this Gaussian prior distribution. So this is how they construct this metadata set. And later what they do is that they train this GPT-2 model using this metadata set. And here this GPT-2 is a smaller version of the ChatGPT. They train it using this meta loss function, using the next word prediction loss, predict the next y using the prefix, this x1, y1, x2 to predict y2, x1, x1, y1, x2, y2, x3 to predict y3, so on and so forth. After they train this GPT-2 model, they evaluate the test performance of this GPT-2 model on a new independent task. And here is their experimental result. The vertical axis is the test error in the square, or the squared test error. And the horizontal axis is the capital N, is the number of in-context example. The green curve is the performance of the Bayes optimal predictor. So because, well, for a new task, well, we don't know what is a beta. So we need to use the demonstration example to first learn this parameter beta, and then use the beta to form a prediction. And the optimal prediction is given by this green curve, the Bayes optimal prediction. And we know that in Bayesian linear model, optimal prediction is given by the ridge regression estimator with optimal ridge parameter. And as we can see, the performance of the pre-trained transformer has a performance the same as the Bayes optimal prediction. And if we look at some other prediction rule, like ridge regression with suboptimal regularization parameter, the performance is worse than the performance of the pre-trained transformer. So this is a very surprising experiment. It says that, well, this pre-trained transformer can not only perform in-context learning, but it performs in-context learning in some optimal way. And today, I would like to first theoretically explain why can this pre-trained transformer perform this in-context learning task. So to theoretically understand why in-context learning can be performed by pre-trained transformer, we first need to dig into the architecture of a transformer. So a transformer is a sequence-to-sequence neural network, where the input of the neural network is a sequence of vectors hi's, where each hi is also called a token. And after passing through the transformer, the output is another sequence of vectors h1 prime to hn prime. And for in-context learning, eventually, we want the neural network to output a estimator y hat. And we use a simple readout function, which is a linear function, to convert this h prime to a y hat. So in this page, I just treat this transformer as a black box, and I specified the input and output format of this transformer. And in this slide, I would like to open up this black box and talk about the inner structure of a transformer. So a transformer inside the black box, it is an alternating composition of feed-forward layers and attention layers. I use notation FF to denote feed-forward layer with parameter W, and ATTN to denote the attention layer with parameter A. So the parameters of this transformer is just concatenation of these W's and A's across different layers. The feed-forward layer is relatively simple. It is a sequence-to-sequence neural network where it is a token-wise function. The feed-forward layer updates each token HI by a one hidden layer neural network with parameter W1 and W2. So it updates this HI by first multiplying W1 and composite on the activation function sigma, which is chosen to be ReLU in our experiment and the theory, and then apply a parameter W2. So the feed-forward layer is a token-wise mapping. The ith output token HI prime only depend on the ith input token HI. So the feed-forward layer is relatively simple. What is a little bit more complicated is this attention layer. So the attention layer has parameter Q, K, and V, and it updates each token HI by this QKV interaction. Well, you first look at the inner product of QH and VH, and the composite on an activation function, and in our experiment and theory, we choose it to be ReLU. And then multiply this VH and take the average and take the sum over the heads. So intuitively, you can think about the attention layer to be the following. So the ith output token is a linear combination, it's a weighted linear combination of all the input token up to a transformation. And the weight is given by the score, and the score is computed using the inner product of the input token and the output token, and the composite on the activation function. Okay, so this is the attention layer of a transformer. The whole transformer architecture is just an alternating composition of attention layer and the feed-forward layer, and eventually we use a readout function to extract the estimator y-hat. Okay, so here I have finished introducing the architecture of a transformer, and next I would like to explain how we can use this transformer for in-context learning tasks. So let's assume that we have a data set xi, yi, which are IID following a generalized linear model. This generalized linear model assumption is just an example for illustration. We assume this yi is a generalized linear function of x, where the f is a nonlinearity function, and the input is the inner product of xi and w star plus noise. Here, this w star is a parameter that is unknown to the transformer. And the transformer takes this whole data set as an input, where the ith input token hi, we take it to be the concatenation of xi, yi, and the 0. And here, this 0 is called a scratch pad. And it is very important, as we shall see later, while all the computation will happen on this scratch pad. The last input token of this transformer is special because we want to calculate the estimator of this new y. So we take this y place of this last token to be 0 as a reserved slot for output. And we hope that after passing through the transformer, this 0 place become a y-hat, which is an estimator of the new y. And we read out this place. So the overall output is this y-hat. And our hope is that there exists a transformer such that this y-hat is a good estimator of the new y. And the theoretical question is that why there exists a transformer that can output an estimator that is a good estimator of the new y. So to solve this question, let's first imagine how statisticians approach this task. Suppose a statistician encounter a dataset and assume to be a generalized linear model. And then the statistician would first do is to estimate this parameter W star by writing down an empirical risk associated to the dataset. So writing down the empirical risk associated to the dataset, this is given by the average of the loss function on this X transpose W and Y, where this W is something we would like to use to estimate this W star. And the statistician would perform optimization on the empirical risk, maybe by minimizing the empirical risk using gradient descent algorithm. And after performing gradient descent, then the statistician would transform the gradient descent iterate, the last iterate of the gradient descent, transform it to an estimator of the new Y. So I want to argue that the transformer architecture, the forward pass of the transformer, could perform similar thing as what a statistician can do. So I would like to illustrate in this slide that while this attention layer, this one attention layer can implement one step of gradient descent. Okay, so here this is the formula for one attention layer. This is an update of the H token by this QKV interaction. And here this is the formula for gradient descent. This is an update of this W by this XWY interaction. You can see that these formulas, these two formulas are somewhat similar. And I can make these two formulas to be more similar by do the following task, by do the following. So I can take this HI token to be the concatenation of X, Y, and W. And here, remember that the input of this H is XY0, where the 0 place scratch pad is, we use the 0 scratch pad to record the gradient descent iterate. If we take this construction, we can find these QKV matrices to be the following. We can find the Q matrix such that after multiplying this token, it becomes W1. The K matrix multiply this token become XY, and the V matrix multiply this token become 00X with some coefficient in front. By doing this construction, we can show that this attention layer become here this formula. And this formula become more similar to the gradient descent iterate, except that, well, the gradient descent iterate here has this partial derivative of loss function. And here, this attention layer formula has this one hidden layer neural network. And it's an update of this W by this one hidden layer neural network interact on this X. And then we can just call a universal approximation theory for the partial derivative of this loss function, so that you can see that this one hidden layer neural network can efficiently approximate this partial derivative of loss function. And here, this approximation is approximating a bivariate function. So there's no curse of dimensionality in this approximation. Okay, so here I want to remark that this is just an approximation result. It doesn't say like a pre-trained transformer is just doing, while attention layer is doing this one-step gradient descent. It just says that while this transformer has the capability to approximate this gradient descent iterate. Well, you can imagine that while each attention layer can approximate one-step gradient descent, so this recursive attention layer transformer can approximate this layer by layer, can approximate this gradient descent step by step. And we can use the last attention layer to approximate this transformation from the estimator of W to the estimator of Y, so that we can use the transformer to output a Y hat. Okay, so this says that while the forward pass of this transformer can perform the gradient descent iterate and extract this Y hat, similar to what statisticians do when analyzing this generalized linear model task. And you may wonder what happens to this feed-forward layer. So we can show that this feed-forward layer can approximate this proximal operator. So this alternating attention feed-forward transformer could approximate this proximal gradient descent iterate. And remember these proximal gradient descent algorithms are good algorithms for solving lasso, well, regularize the ERM problem like this lasso. So this also says that, well, this alternating attention and feed-forward layer transformer can efficiently solve this lasso problem for sparse linear model. So not surprisingly, we can convert this construction into a theory. So the theorem says that, well, there exist three different transformers that respectively can implement the ridge regression estimator, logist regression estimator, and lasso estimator, which achieve the optimal statistical efficiency. The statistical efficiency is upon this in-context learning task. And here, the important thing is that, well, this transformer has controlled size, where the size parameter of the transformer is given by this embedding dimension D, number of layers L, and number of attention head M, feed-forward layers with D prime, and the norm of these parameters. And for this theoretically constructed transformer, all these size parameters are well controlled by the size of the problem-dependent parameters. Okay, so it says, well, there is an efficient approximation for a transformer for this in-context learning task. There's no curse of dimensionality. And of course, up to now, this is still an approximation result. And in the next slide, I would like to convert this approximation result to a learning result. And suppose we have a metadata set, ZJs, they are IID following some distribution, and this distribution is upon the data set xi, yi, and this data set, they are IID following some task, like, for example, the sparse linear model. And we construct this empirical risk minimization for this meta training task by looking at the average of the meta loss and the minimization over the transformer class. So here, this is a theoretical empirical minimization process, while in practice, you can solve this minimization problem by meta training this transformer using this Adam algorithm, for example. And suppose we are able to find the minimizer of this empirical risk. Then the minimizer has the following theoretical guarantee. We can show that, well, the performance of this meta training learned transformer has the performance as good as the performance of this theoretically constructed transformer plus a term that vanishes as the number of meta sample goes to infinity. And on top, here this complexity is polynomial with respect to the size of this transformer. Okay, so combining the approximation result and generalization result, I can get a overall result. And let's give an example. Let's say, well, this meta training task is the sparse linear model. And the task has capital N number of in-context example and the little n number of meta samples. Then, well, we train this transformer using this metadata set, and the learned transformer can perform this in-context learning task for sparse linear model as generalization error that is S log D over capital N. Here, S is the sparsity of the sparse linear model, and the capital N is the number of in-context example. So you can see that here, this error is the generalization error, is the optimal generalization error of the lasso estimator. And here, there's additional term that is the generalization error of the pre-training task, which is given by here, which is this term here. And here, the complexity is d to the fourth. So this is d to the fourth is not optimized. We didn't try to optimize this parameter, this complexity. But as you can see here, this generalization error is without curse of dimensionality. So this is like what we want to achieve. We want to achieve a learning result for this in-context learning task without the curse of dimensionality. And remember that the way we achieve this is by viewing this transformer as an algorithm, as an algorithm approximator that approximate this proximal gradient descent algorithm. And by taking this algorithm approximation perspective, we avoid the curse of dimensionality for transformers in this in-context learning task. Okay, so this is the first example I would like to talk about for using transformer doing in-context learning tasks without curse of dimensionality. And I would like to then discuss the second task, discuss a similar story upon the diffusion model. So let me first give a intuitive example for what this diffusion model can do. So here is an interaction of me with this DALL-E model. I just prompt a sentence, a cartoon displaying a cat riding on an airplane during night from his home to a castle. And then the diffusion model, this DALL-E model, returns me 4 different images. You can see that all these images correspond to the sentence, but they have some difference in the image. So the diffusion model is modeling the distribution of the image. You can sample from this image distribution. Mathematically, you can say that, well, this diffusion model is solving this generative modeling task. And as for now, ignore conditioning on the sentence. Let's for now focus on how this diffusion model generate this image sample. So the generative modeling task is the following. We want to learn a model from a data set. Well, the data set is xi's. We assume these xi's are ID following some image distribution mu. Well, this distribution is some underlying distribution that generates this image data set. And we want to learn a model so that we can generate a new sample x hat that also follow this distribution mu approximately. The diffusion model solves this generative modeling task using a 2-step procedure. In the second step, the diffusion model first starts from a Gaussian white noise and apply the denoising network sequentially to this Gaussian noise. And then you can see that image become more and more clear. And the diffusion model used the last step of this sample as the final generated image. And why I say this is the second step of the diffusion model, because there is a first step to train this denoising network. And the denoising network are trained from using the noisy image to predict the clear image. So where does this noisy image and clear image come from? Well, the clear image comes from our data set, and the noisy image comes from that human manually adding Gaussian noise to the clear image. So you can get noisy image and clear image pairs. So this is how intuitively this diffusion model solve this generative modeling task and generate this sample. Mathematically, you can turn this 2-step procedure into this empirical risk minimization and stochastic differential equation formula. So the first step is learning this denoising function, this neural network. And well, mathematically, you can say this is learning, well, people call this approximate score function by minimizing on this supervised learning task, where people use this noisy image to predict the noise. So predicting the noise is similar to predicting the clear image, and people call the result approximate score function. And in the second step, people solve this stochastic differential equation where the drift term is given by the score function. So this running the stochastic differential equation from Gaussian noise is equivalent to say you apply this denoising network sequentially on this noisy image and eventually get a clear image. And the people use the last step of this SDE as approximate sample. So theoretically, you can show that, well, suppose there is infinite sample, suppose the function class is super rich, and there's no discretization error, and the time is infinity, then you can show that the last step of this SDE exactly follow the image distribution where the mu is how you generate this sample, how you get this data set, how you generate this training data set. So we will not prove this theorem, but our question is, well, in practice, we only have finite sample and a finite neural network class. How does this theorem behave when we only have finite resources? So to understand this, we need to dig into the first step more carefully. So in the first step, while we train an approximate score function by empirical minimization over this neural network, and we know that the population risk minimization of this objective function is given by the population score function, which is given by the gradient of log mu t, where this mu t is the distribution of a noisy image. So because this gradient of log mu t, well, this gradient of log distribution is called a score function in statistics. So this is why people call it a score function. And our question is like, when this score function can be efficiently learned by neural network through this empirical risk minimization process. And while the classical viewpoint using this function approximation viewpoint can solve this task in some way. So the classical function approximation viewpoint can solve this task in the following. So suppose this distribution mu, this image distribution has a smooth density on the cube. If this is the case, then the score function is also smooth. Because neural network can efficiently approximate smooth functions, so neural network can approximate this score function. So this is a classical function approximation viewpoint for this problem. The challenge of this classical viewpoint is that, well, this natural image distribution is high dimensional. And for efficiently approximate this score function, it requires that, well, there may be a curse of dimensionality unless the target image distribution is super smooth. And this is not a very realistic assumption. So to tackle this curse of dimensionality challenge, well, we propose an alternative approach for this task, for thinking about how neural network can approximate this score function efficiently. Our approach is given by the following three ideas. So first, we model this natural image distribution as a graphical model. And notice that, well, in the literature, people often use graphical model to model this natural image distribution. And in graphical models, people often use variational inference algorithm to compute the score function. And these variational inference algorithms often admit efficient neural network approximation. So this is the approach, this is the high-level approach that we use to tackle this curse of dimensionality challenge. Let me give two examples. So the first example, this is a graphical model that we use to model the image distribution, which is this async model. So we model the pixel of the image as a node in the graphical model, and adjacent pixels gives an edge of the graphical model. So the image distribution is modeled as a 2D lattice async model. And mathematically, while this distribution is given by this async model, there is exponential of a quadratic potential. And this is not a Gaussian model because like x is on the cube instead of x is not on the real line, it's on the solid cube, on the discrete cube. And on this async model, we know that, well, the score function is related to the denoising function, and the denoising function is given by the posterior expectation under this tilted distribution. Here, this tilted distribution is an async model tilted by a linear function of the observation z. We know that, well, to compute this denoising function, statisticians can use this variational inference algorithm. And here, this variational inference algorithm is an iterative algorithm that only involves matrix vector multiplication and pointwise linearity. And as you can see, well, this variational inference algorithm can be efficiently approximated by ResNet, recursively approximated by this ResNet, where each step is given by the one hidden layer neural network. So here is this illustration figure to demonstrate that, well, this one-step variational inference algorithm can be efficiently approximated by one step of this ResNet, one layer of the ResNet, so that a multi-layer ResNet can efficiently represent this variational inference algorithm. So not surprisingly, we can convert this construction into a theorem which has guarantee on the estimation error of the score function. And this page is a little bit dense, so let's skip and talk about a more concrete example. So let's consider the example of the Easing model where the coupling matrix A is given by a Gaussian random matrix. So this is called the Sherrington-Kirkpatrick model, a spin glass model that was proposed by physicists. And the physicists have analyzed this model a lot and has understand how to sample from this SK model. And for this model, we have known that, well, in the high temperature regime, the variational inference algorithm can be used to estimate the denoising function with the estimation error that is up to an error that is conjectured to be 1 over dimension d. And let's take this as a conjecture for granted and do some heuristic calculation. We can see that to achieve epsilon square sampling error, we need the sample size n to be polynomial, well, to be 1 over epsilon to the 18th. So this 18 is not a number that we have optimized, but the point is that, well, this is a polynomial on 1 over epsilon. In comparison to the function approximation viewpoint, the required sample size is 1 over epsilon to the power of d, where d is the dimension of the image, and in practice, the dimension of the image is at least a few thousand. Okay, so using this, so that means using this graphical model assumption and using this algorithm approximation perspective, we get a theoretical result on the estimation on the sampling error that overcome the curse of dimensionality. Okay, so this is how we overcome the curse of dimensionality for diffusion model in the Easing model assumption. But in practice, practitioners often use a special architecture to fit the score function, and the architecture is called the UNet. The UNet is a very special architecture which includes an encoder and a decoder on long-skip connection structure. So for the encoder, there is convolution operation downsampling, convolution downsampling, iterating these two steps. And for the decoder, there is convolution upsampling and iterating these two steps. And there is this long-skip connection that connects the earlier layer of this encoder to the later layer of this decoder. So we want to understand why in practice, practitioners use this UNet to fit this, to serve as the denoising function, the score function of this image distribution, and works well. So to explain this, we need to come up with a generative model for the image distribution. And we propose to use this generative hierarchical model to serve as image distribution. So the generative hierarchical model is a tree-structured graphical model where the tree, there is a distribution on the tree, and the root of the tree stands for the highest level concept, like animal, cat or dog. And then the generative model recursively generates lower level features by going from the root to the leaves. So there are intermediate level concepts like style and background, eye, hair color, and the posture. And finally, we reach the leaves of the tree, which represents the lowest level, the pixel level representation of the image. So for this generative hierarchical model, in the literature, people have studied how this model can capture the distribution of the image. And we assume that the ground truth distribution is given by this generative hierarchical model. And suppose a statistician look at this generative hierarchical model and want to solve the denoising task, then the bipropagation algorithm is what they want to do. So given this pre-structured graphical model to denoise on this model, people can write down this denoising algorithm, which is a belief propagation algorithm. So this is the mathematical equation. Well, it looks complicated, but if you just write down, if you draw this mathematical equation into a figure, you'll find that, this figure is just very similar to the UNet architecture. There is this convolutional neural network, average pooling, convolutional neural network, average pooling with downsampling, and there is a encoder, there is a decoder, and there is this landscape connection structure, which mimic the UNet architecture. So we can construct this neural network. Well, let's say we take this neural network, this UNet, to learn this denoising function. Then, we can show that, it can approximate this belief propagation process of this denoising function, so that this neural network can capture this denoising function. This is how we approach this problem for when we model the distribution to be a hierarchical model. And you may wonder why we cannot just use the original bipropagation to serve as the denoising function, why we need a neural network. Well, the reason is, robustness under model misspecification. Well, for using this bipropagation to serve as the denoising function, we need to know the architecture. We need to know the structure of the model at the beginning. If there is model misspecification, then the bipropagation may not may not perform well. But for neural network, it is a non-parametric approach. And even if there is model misspecification, the neural network can adapt to the misspecified model, so it can still perform well. So theoretically, we can show that the estimation error of the score function using this UNet can be well controlled, which is a polynomial function, which is the estimation error is a polynomial of problem-dependent parameter. Okay, so I finished introducing these two examples, language model and diffusion model, and illustrate how this algorithm approximation perspective can avoid the curse of dimensionality in this language model and diffusion model. Next, I would like to discuss the difference between the function approximation and algorithm approximation paradigm. So, people may wonder why there's a difference between function and algorithm. Well, actually, functions and algorithms are tightly connected. So any algorithm will correspond to a function because, algorithms are just the composition of operations which are just functions. But actually, one function doesn't correspond to a single algorithm. So for any fixed function, there are multiple algorithms to compute this function. For example, if you want to solve a linear system, there are Gaussian elimination algorithm or gradient descent algorithm can solve this linear system. So that means a function can correspond to multiple algorithms. And there are also functions that are not able to compute it by algorithms. A famous example of this kind is the halting problem of the Turing machine. There's no algorithm can be used to compute that function. And there are functions that can be computed using algorithm, but cannot be computed efficiently. A famous example of this kind is the three-set problem, which is conjectured not to be able to compute it by polynomial time algorithms. So that being said, the set of functions and algorithms are different. And the characterizations of functions and algorithms are also different. To characterize a function, while people use smoothness, dimensionality, sparsity, and degree of polynomials, but to characterize algorithms, people often use number of steps, types of operations, and the stability. So because the way of characterization of algorithms and the functions are different, so the paradigms for function approximation and algorithm approximation are also different. So suppose we want to use the function approximation paradigm to approximate a target function using neural network. What people often do is to calculate the smoothness of the target function, and then call the universal function approximation theory for smooth functions to approximate this function. And this often encounter a curse of dimensionality. But suppose people want to use this algorithm approximation paradigm to approximate this target function, what we want to do first is to decompose this target function into a few steps that can be computed using like simple operations, composition of simple operations, and show that each block of this operation admit efficient neural network approximation. And often this can avoid the curse of dimensionality. The example of language model and diffusion model I provided in this talk are examples to show that this algorithm approximation paradigm can avoid the curse of dimensionality in approximating this diffusion model, this denoising function, and this in-context learning estimators. Okay, finally, I would like to talk about some other benefits in viewing neural networks as algorithms. So the first benefit is that, well, this algorithm approximation viewpoint can immediately derive approximation hardness result. So there are some functions that is known to be hard to be computed by to be computed, and the example of this kind is this Bayesian linear model with some complicated prior. We know that for this denoising function in this model, the Bayes estimator is computationally inefficient. And because, well, we know this is computationally inefficient, so we know that like polynomial sized neural network cannot compute this function efficiently. So there is a approximation hardness result implied by this computational inefficiency of this Bayes estimator. The second benefit of this this algorithm approximation perspective is promoting interpretability of this neural network. So by interpreting this neural network as algorithms, we can dig into the black box of this neural network and try to interpret where each operation of this neural network, what does it mean in doing this computation. And the third benefit of this algorithm approximation perspective is the guide architecture design. So an example of this kind is the paper by the group of Ima at Berkeley. They created a white box transformer called Create. And this architecture is, this is a transformer that is like designed, guided by the algorithm unrolling principle. And this Create architecture has more interpretable architecture than naive transformer. And the performance is comparable to vision transformer on image classification tasks, but it can learn better representation than vision transformer. Okay. So, well, let me summarize my talk. So I've put forward a new perspective on the role of neural network in generative AI models. I say these neural networks in generative AI models should be more interpreted as an algorithm than a function. And this can explain the expressivity of neural networks in language model and diffusion model and avoid the curse of dimensionality. and it opens up many interesting research directions, including deriving approximation hardness results, promoting interpretability, and guiding architectural design. Okay, so I would like to use the last part. Finally, I would like to promote a workshop that I have co-organized. That is one day before the JSN, and the workshop, we have this new workshop called Frontiers in Statistical Machine Learning (FSML) workshop. This is like August 2nd, 2025, one day before the JSN. And the JSN this year is in like Tennessee, Nashville, and the workshop is just co-located with the JSN in Vanderbilt University. And this workshop will feature invited sessions with two topics: the science of deep learning and statistical learning from heterogeneous data source and generalization. And importantly, we have a call for submissions. We invite submission to this workshop, and once accepted, we will invite the group to present posters at the workshop. And for more information, you can check this link. So I will copy this link in the chat so that you can take a look at this more information for this workshop. Yeah, thank you. So this finished my talk. Thanks for the audience, and thanks again for the invitation.